In this lecture, we will keep considering geometrical objects in R3. Subvector spaces of R3 can be of 4 different kinds. According to their dimensions, we start from a unique zero-dimensional subspace, which is just the zero vector. One-dimensional subspaces, which geometrically are lines through the origin, through the zero vector. And then there are two-dimensional subspaces, which are planes through the origin. And lastly, there is a unique three-dimensional subspace, which is R3 itself. By translating them, we obtain geometrical objects, whose dimension we define to be the one of the vector space, called its homogeneous component, of which they are the translated. In lecture 12.3, we discussed planes in R3, whereas now we consider lines. Definition: a line in R3 is a translated of a one-dimensional subspace. Just like for planes, we have the in-coordinates and parametric expressions of lines. Let's see what they are in detail. The in-coordinates expression is the following. L is, we open curly bracket as usual for all in-coordinates expressions. We are going to list all the vectors that belong to L, all the points that belong to L. And since they are elements of R3, we impose conditions on their coordinates, x, y, and z. They have to satisfy two linear equations simultaneously. And moreover, there must be a condition on the coefficients of the variables, which we denoted with two indices in order to impose this condition more easily in terms of matrix notation. The condition is that if we let these coefficients form a matrix, with the first row the coefficients of the first equation and the second row the coefficients of the second equation, this matrix must have rank 2. Now let's see why this is supposed to be a line. Let's start from the vectors x, y, z in R3 that satisfy just the first equation. Well, in the previous lecture, 12.3, we have seen that all these points form a plane in R3. If we consider the points that satisfy both these equations simultaneously, then we are looking at the points that are in the intersection of these two planes, one with the defining equation given by the first equation and the other with the defining equation given by the second equation. Okay, so the intersection of two planes may be of three different kinds. So the first kind is if the two planes are parallel and they have no intersection points, then these two planes, then L is going to be an empty set, the empty set, which of course is not a line. The second possibility is that the planes are again parallel and they have an intersection, at least an intersection point. Well, in that case, the two planes coincide and L is one of these two planes, which again is not a line. So we want to make sure that the two planes are not parallel. Okay, so one can show using the theorem RC that we have stated when we covered the systems of linear equations, that if the two planes are not parallel, the only possibility is that their intersection has dimension 1, so it is a line. And the condition in order for these two planes not to intersect is precisely this. Why is this? Because, as we noticed in the previous lecture in 12.3, the coefficients of the variables in the expression of a plane in coordinates are the normal vector to the plane. And imposing that the rank of the matrix form with the rows being equal to the normal vectors implies that the normal vectors are linearly dependent one with the other, so one is not multiple of the other. And this means that the planes are not parallel. So this condition is equivalent to the fact that the planes are not parallel. Therefore, by the RC theorem, the dimension of the solutions of this system of linear equations must be 1. Let's see what is the expression in parametric form. And this is going to be very easy. It's simply a homogeneous part, which is a one-dimensional subspace of R3, and this homogeneous part is expressed by providing a basis. Well, since it is just a one-dimensional subspace, a basis is formed by a non-zero vector inside that one-dimensional subspace. So it's going to be of the form vector space generated by V for some non-zero V. And then we have to translate it to one point of this line. So P is going to provide the translation of this one-dimensional subspace, the homogeneous part, to the line we are considering, and we can translate it to any point of the line. So given any point of the line P, this P will provide the translation of the homogeneous part. So this ends up the expression in parametric form. Let's see an example. Let's find a line L passing through the point -1, 3, 2 and parallel to the vector 1, 1, -2. The easiest way to express L is in parametric form. The condition on the parallelism is immediately imposed on L by taking V to be 1, -1, -2 in the expression L equals to vector space generated by V plus P. Remember that this is the parametric equation of a line in R3. We have to figure out, therefore, the vector V and the vector P. Now both of them are provided by this example. Having a line parallel to vector V, well, then we can just take V as the homogeneous component of L, or our line L, and take the vector space generated by V. And then knowing a point inside that line, which is -1, 3, 2, well, then we take that point to be the translation of this one-dimensional subspace. Therefore, it is just a matter of plugging in these two values of vectors inside this expression. Hence, L can be expressed in parametric form as the vector space generated by 1, 1, -2 plus the vector -1, 3, 2. This expression can be further expanded as L equals to the vector space generated by this vector is the set of linear combinations of the vectors that form a basis or generators of the subvector space. In this case, a basis comprises just one element, which is this vector. Therefore, linear combinations of a unique vector are just multiple of these vectors by a scalar. So here we have L is lambda times 1, 1, negative 2, with lambda that ranges inside R, plus the vector negative 1, 3, 2. Again, set theoretically, these can be re-expressed once again as we open curly bracket. We just expand this set by multiplying through the lambda inside the vector's coefficients. And at this point, we also sum this vector up in the expression, so that we get a generic vector in the line of the form lambda minus 1, so it comes from lambda times 1 minus 1, second coefficient lambda plus 3, lambda plus 3, and then negative 2 times lambda plus 2, negative 2 times lambda plus 2, with lambda that ranges in R. Or equivalently, this is a more commonly used parametric expression for a line. L equals, so we open a curly bracket because these conditions must hold simultaneously. The x-coordinate of a generic point in L has to be of the form lambda minus 1, which is this. The y-coordinate lambda plus 3, which is this. And the z-coordinate negative 2 lambda plus 2, where lambda ranges in R. I would like once again to remark that the expression in parametric form, although in this case has been almost immediate, it does not lend itself to an easy way to use it in practice. This is because, for example, suppose that we have to find whether a certain vector belongs to L or not. I don't know, vector 3, 5, 8. Does it belong to L or not? That is the question we want to answer. Now, well, in order to answer to this question, we have to plug in for x3, and then for the y coordinate I've chosen, and then for the z coordinate I've chosen. And if this system will have a solution, then the point will be in L, otherwise it will not be in L. To answer this question, I have to solve a system of linear equations, and it takes a lot of time and effort. A better way to express a line, just like it was the case for the plane, would be to find the coordinate expression of L. Let's do that right now. Remember that to express L, a line L in coordinates, we need the equations of two planes whose intersection is L. We focus on the homogeneous component first. L0, the homogeneous component, has the same expression as L, except that in the defining equations there are no constant terms, there are just the variables parts. Then we find d1 and d2, which are the constant terms, by imposing that the vector negative 1, 3, 2 belongs to both planes. This was one of the conditions given in the example. Now, since L0 is a subvector space, we can use linear algebra to determine it. Suppose we can find the two vectors R and S with the following property. They are both perpendicular to 1, 1, negative 2. Remember that 1, 1, negative 2 was the vector that generated L0. In the example we stated before, we wanted to find a line parallel to 1, 1, negative 2 and passing through negative 1, 3, 2. Thus, since L0 is the homogeneous component of our line, we can take L naught to be the vector space generated by 1, 1, negative 2. Now, if we have two vectors that are perpendicular to this, and they are linearly independent, let's say that they generate a plane, then we can take, I claim that we can take the coefficients of these planes to be R and S respectively for the first equation and the second equation. Now, why is this? Notice that L naught, which is the vector space generated by 1, 1, negative 2, as I just said, is certainly a subvector space of the plane H1, whose defining equation is given by the coefficients of R. Indeed, in this form, H1 are all the vectors in R3 that are perpendicular to the vector R. So in particular, since R is perpendicular to 1, 1, negative 2, 1, 1, negative 2 must belong to H1. Therefore, also the whole subvector space generated by this vector is a subvector space of H1. So L naught is a subvector space of H1. For the same reason, L naught is a subvector space of H2. Therefore, L naught is a subvector space in the intersection of H1 and H2, which is precisely this set right here. But then L naught is exactly the intersection, simply because the intersection of H1 and H2, assuming that R and S are linearly independent. So there is this condition missing in the statement. So yes, R and S are two vectors such that the vector space generated by them is perpendicular to 1, 1, negative 2, but they have to be linearly independent. So this must be a plane. So in that case, L naught is precisely this set where the coefficients here are taken by R and S. Now let's find R and S explicitly given the data we have. By definition, the vector space generated by R and S that we are looking for is the plane whose vectors are perpendicular to 1, 1, negative 2, exactly as we stated before. The assumption was that both R and S were perpendicular to 1, 1, negative 2. So if I take the plane described as all the vectors that are perpendicular to 1, 1, negative 2, inside there I will find R and S. Now, I simply need to take then a basis of this plane, and then I will name one of these vector bases R and the other S. A basis of this vector space is negative 1, 1, 0, and 2, 0, 1. See lecture 12.3. We already explained how to find the basis of a plane written in coordinates. We just have to express one of these coordinates in function of the other two, and then choosing the other two alternatively, having the values 1, 0, and 0, 1. In this particular case, R corresponds to y equals to 1 and z equals to 0, and then x is forced to be a certain particular value from this expression. And here S corresponds to y equals to 0 and z equals to 1. So now we have found R and S, and we can directly express L naught as the line, the one-dimensional subspace, that in coordinates has the following expression: negative x plus y equals to 0 and 2x plus z equals to 0. So that the expression of L is going to be of the same form as before, but we have to add two constant terms, d1 and t2, to the equations, and then now d1 and d2 will be evaluated by imposing that the other condition we had in the example, negative 1, 3, 2, belongs to L. From the first equation we derived that d1 plus 3 plus 1 equals to 0, and then these other expressions. So d1 equals negative 4 and d2 is 0. And this completely determines the expression of L as negative x plus y minus 4 equals to 0 and 2x plus z equals to 0. Notice that if now we want to see whether a certain point belongs to L or not, well, we don't have to solve any system of linear equations. We just need to plug the values of the point we are wondering about inside the variables of these two equations. If they are both satisfied, then the point will be in L, otherwise it will not be in L. This is a particular example in which we really want to find the expression of our line in coordinates, but it is hard to find it right away in one step from the data that we are given. In this particular example, it was easier to first determine L in parametric form and then transform the parametric form in the coordinates form in order then for this data to be used in all sorts of applications.